In this video, I will elaborate on a first method to solve systems of linear equations, which is the Gauss elimination methods. Now, the Gauss elimination method, which was named after Carl Friedrich Gauss over here, as we already mentioned, this is a direct method, which means that we try to cast this linear system A, the matrix A times X is equal to B into a form which we can easily solve, and then we try to solve it in one step. And that is what we try to do. So first we convert the system into a upper triangular form, or an echelon form as it's also known, using steps of forward elimination. And that's what Gauss elimination actually is. So using row operations on the matrix, we try to convert it into this upper triangular form. So we try to make all the entries below the main diagonal equal to 0. And so we see that this impacts all equations except the first one. So we see here that these coefficients are changed and the right-hand side element is changed as well. And also for this third row, both the coefficient and the right-hand side have changed. Now, once we have it in upper triangular form, we can easily solve this system using backsubstitution. So starting from the last row, we work our way upwards and keep substituting in the freshly computed value for the unknown in the previous equation. And we've already seen how this works. So we start out with calculating x3. We plug x3 into the equation for x2, and we plug then x2 and x3 into the equation for x1. And that allows us to solve this system. Note that this is quite similar to how you would solve the system by hand. And we will discuss now how we do this within a computer using programming. Let's first look at an example, or a specific way in which we can convert this system AX is B, a dense system, into an upper triangular form. So we start by selecting each of the columns, and we start with column 1, where we try to remove all the non-zero entries below the main diagonal. So below this A11 coefficient that can stay there, but A21 should be rendered 0 and A31 should also be rendered 0. Now some terminology. We call in this case, when we're doing this process of removing these elements from the matrix, we will call this first row the pivot equation, because that is the row we'll be using and that will be subtracting or adding to other rows in order to make zeros in those rows. And we call A11 the pivot coefficient. So the first thing that we can do is we try to remove this A21 and put it to 0. Is by subtracting from row 2, row 1, but we multiply it with A21 divided by A11. And we see that in that case, this element will be 0. These elements over here in red in general are not 0, but that's no issue because we just want to make zeros in the first columns in this first step. And we see that this element, and the third element, the element in the right-hand side vector are impacted. To go to the third row, well, we do a very similar approach. So from the third row, we subtract the first row, multiply it with the ratio between A31 and the pivot coefficient A11. And also that will make a 0 in this spot in the matrix and will impact this element, and this element in the right-hand sides. So now we see that the first row is done. So we have zeros below the pivot coefficient. So I just copied that matrix over here, and then we move on to the next column. And we repeat this process. So again here, below this pivot coefficient A22, or A22 prime more exactly, we want to get only 0. So we want to get rid of this A32 prime. and put it to 0. So we say now that the pivot equation is this second row and the pivot coefficient is A22 prime. So what we do is completely analogous to our first column. For the second column, we subtract from this third row the current second row multiplied with the ratio between this coefficient and the pivot coefficient. And in this case, I see there's a slight typo, so this should be A32 on the slide. Because if we do that, then this element will be put to 0. This element is in general non-zero, but it has changed from here to here. And also this element has changed. And we see now that below the pivot coefficient in the second column, we have only a 0. Now let's take a look at column 3. Well, in this case, column 3 is the last column. Again, you can define a pivot equation or a pivot coefficient, but it doesn't make sense because for the last column, that doesn't require any further work, as the system, as we see it here, is already in upper triangular form. So now we have our system in upper triangular form. We do back substitution, so we work our way up, starting from the bottom to compute x3, x2, and x1. So the first equation, x3 is equal to b33, and again there's a slight typo here. This should be double prime. So this is b3 double prime divided by a33 double prime. And then we move on to the second row. In the second row, we can easily plug in the newly computed, well, the freshly computed, let's say, value for x3, which gives us here an explicit equation for x2. So we just say that this is a22 prime times x2 plus a23 prime times x3 is b2 prime. And we can make this explicit for x2. We can just fill in the values because b2 and these a coefficients are known, and also x3 is known from this previous step, which gives us x2, and we can repeat this process for x1. Let's look at a specific example, a numerical example of how this works. And here we have this linear system, which was also featured in the introduction. We can recast this into a matrix form, which we will then solve using Gaussian elimination. So step 1 is the forward elimination. So we try to convert the matrix A here into a triangular form, a upper triangular form in the case of Gaussian elimination. So what we do is, well, first we start with column 1 and we try to get zeros in this coefficient and this one here. So what we do is, well, we subtract from row 2, row 1, multiplied with the ratio of this element and the pivot coefficient, which is 1 in this case. So that's simply minus 2 times row 1. And we see that we get a 0 over here, so that's nice. And we get non-zero elements over here in general, but that's okay. We're not interested in those at this point. We go to do a similar thing for row 3. And in row 3, well, we see that 1 and 1 are equal, so we can just subtract row 1 from row 3, which renders this coefficient equal to 0. So now we're done with the first column and we move on to the second column. So for the second column, well, we need to get rid of this element over here, and we see that we can do this by adding twice the second row to the third row, which makes this coefficient equal to 0. And in that sense, we have now a triangular system already, because the last column, we don't need any further action on that because we have no entries below the last diagonal element here. So we have our matrix in upper triangular form, and we can proceed with doing back substitution. So for back substitution, we start with the final equation. x3 is equal to minus 10 over minus 5, so that's equal to 2. This equation, well, we can make that explicit for x2. That will be minus 3 plus 3 times x3 divided by 1, which is this diagonal coefficient. We plug in 2 into this equation. Well, we get minus 3 plus 6 is 3 divided by 1 is 3. And finally, we can do the same for the first equation. So we get 6 minus 2 is 4, minus 3 is 1, divided by 1 is 1. So our solution is 1, 3, and 2 for x1, x2, and x3. Now that we've done an example by hand, let's take a look at how this could possibly be converted into a computer program. And here we see a kind of pseudocode, or it's almost MATLAB code, for implementing the Gaussian elimination method in a computer or in MATLAB. So the algorithm's purpose is to solve AX is B for known A and known B to obtain X, where A has n rows and n columns. And there are two steps to this algorithm. So first we start with Gaussian elimination, after which the matrix A will be recast into upper triangular form. And then we do a back substitution to compute all the components of the unknown vector. So let's take a look and walk through this algorithm together. So here we have a for loop, and we loop over all columns, starting from the first one up until not the last one, because we already mentioned that for the last one we don't really need to do anything. So let's try to be efficient and not include the last one in this loop, but just loop from the first one up until the second to last one, so n minus 1. And in this case, this will be columns 1 and 2. So we start with column 1, and then we say that the pivot coefficient is A11. The pivot row of A will be simply these blue elements over here. That's R1, as we call it here. And then the pivot row of B will be this coefficient B1. Now what we will do is we try to get rid of these non-zero coefficients and make them 0. So we have to proceed with the rows in a sequential fashion. Now, how do we do this? Well, we start from row, column plus 1, because we are interested only in rows below this diagonal. So in this case, this will evaluate to row 2. So we start from row 2, and then we compute this coefficient. So that's the ratio of this coefficient A21 and the pivot coefficient A11. And we can simply subtract from the second row this first row, or the pivot row, multiplied with this coefficient, the ratio of the coefficient that we want to eliminate and the pivot coefficient. And we see that this makes this coefficient equal to 0. And we also have to apply this operation to the right-hand side equation, the right-hand side of the equation as well, of course. So that's done for row. We go to row 3. We do a very similar thing. So we compute this coefficient as the ratio between A31 and A11, and we subtract from this entire third row the first row multiplied with this coefficient. So we're done with the first column, and let's move on then to the next. So here we go for the second column, and we set the pivot coefficient to this A22 prime. We say the pivot row of A is this second row of A, and the corresponding element in the right-hand side vector is this B2 prime. And again, we want to eliminate this non-zero coefficient from the matrix below the diagonal element in the second column. So this is in row equal to column plus 1. So this is row 3. And we again compute this coefficient as the ratio between this former element and the pivot coefficient. And from row 3, we subtract then this coefficient multiplied with the current row 2 of the matrix. And we do the same thing for the third element of the right-hand side vector. Okay, so we finished our we finished converting our system into an upper triangular form. So we have completed this entire loop. So we started from column equal to 1, column equal to 2, and 2 is equal to n minus 1, so we're done. And we see that indeed there is a upper triangular form in our matrix system. And well, let's write this out into explicit linear equations again. So what does the first row mean? Well, that means that a11 x1 plus a12 times x2 plus a13 times x3 is equal to b1. The second row means a22 prime, x2, etc. So this is the explicit recast of this matrix system into linear equations, and that will come handy in a second, as we will see. So now we can proceed with computing the solution x1, x2, x3 using backsubstitution. So we start with the final unknown, so the one in the last row, because this last row equation is trivial. We see here that we can simply divide both sides by a33 double prime, and we get an explicit formulation for the solution x3. So that equation corresponds to the solution of this linear equation over here. Let's move up now to the second row. And we see that for the second row, well, this is the linear equation which we want to make explicit, or we want to solve this for x2. And well, we see that there will be two terms. So x2 will be equal to b2 prime divided by a22 prime minus a23 prime times x3 also divided by a22 prime. So there are two terms, and let's first take into account this right-hand side divided by the pivot coefficient. So again, we say the pivot coefficient is a22 prime, and we can write this as the numerical solution is equal to the b in row 2 divided by this pivot coefficient. So we see that we already have taken into account this term b2 prime divided by a22 prime. But this is not sufficient. In order to get the full true solution, or the numerical approximation for x2, we also need to take into account the contribution of this third column element in the matrix. So we have to loop over the columns starting from the last one up until the diagonal, not including the diagonal, so that we can do using this indexing over here. And in this case, well, the only column that we need is column 3. And what we need to do is, well, we need to subtract from the current numerical solution the ratio of the element with the pivot coefficient times the solution x3, which was already computed. So in that sense, the numerical solution here, x2, will equal this numerical formula. And then we see that the real mathematical formula that we have now entered into the numerical solution is equal to this. This corresponds to our linear equation. So again, we're done here. Finally, we go up one more row in our back substitution. So for row 1, we do something similar. So we know that there will be 3 terms in this case. The first will be b1 divided by a11. So we set the pivot coefficient to a11. We add this term b1 over a11, and then we have to again loop over the columns starting from the last one up until one next to this diagonal. So we start from the last one and then we do the second one. So doing this, well, we do column 3, we add the term for column 3, column 2, and add the term for column 2 over here. And again, we see now that this equation, which is coded into this numerical answer, corresponds to the actual solution of our linear equation. So that's also fine. And then we're done, because we're done with our row loop, we're done with all the loops. And now this vector x will hold the numerical solution to our system.